All right, so anyway, I'll think about something to cheer you up a little bit. Let's see. I think it's supposed to be sunny over the weekend, a little bit cooler. What else? Next week and the week after, we're actually doing a different kind of a schedule for 2 weeks, and they're going to talk to you about it tomorrow. And we're going to try it. There's a blue week and a gold week, and they want to try one of each and see what you like about it. If I happen to have had a big lab planned, 90 minutes would be great for a lab. But I don't have a lab every week for 90 minutes. I don't do that. So anyways, take a look. You know, when they were, I don't know if you can do this. Can you go back? Remember that video you saw where they were trying to figure out chemistry? And what was interesting is that they actually learned a lot of chemistry from air. Remember that, about different gases and oxygen gas and carbon dioxide in it? And they started figuring out things. As a matter of fact, the mole concept actually came from people studying gases. And here's a gas, and they let it react with another gas, and then they measured things. But what kept chemists from the breakthrough in chemistry came when they said, boy, I really wish I knew how many pieces there were in carbon dioxide. This gas that puts out a flame, we can give it a name, but what's it made of? How many of these kind of pieces and how many of these? Well, that was almost impossible for them to figure out how many pieces. How about water? How many things make up water? You ask a third grader here, and yet in 1820s, nobody knew that there were 3 pieces in water, 2 H's and an O. Nobody knew that, but we know it now. It's like nothing for us. But the key to chemistry was in the world, here I am again, in the world of number of particles. They had to know something about the number of particles. And how do we do that? You can't. We couldn't. We couldn't shrink ourselves down to count them. They were too small and there were too many. How do you count a billion, billion, billion? And so I still think it's tremendous that the human mind figured this out, even though it was impossible. It was impossible to count the number of atoms in something, but we did. As a matter of fact, the chapter is called Counting by Weighing. And so I'm going to show you real quickly what they were talking about here, and I'll get back to my thing. Here's they have a little story here in the first page, the second page, and they said, let's pretend that you own a jelly bean store, and you sell really good jelly beans, okay? And people come from all over. They found out about your store. Well, at first, maybe you only had like maybe one customer every 5 minutes or something like that. That's still pretty good. And they would come in and they'd say, well, I'm gonna try them out. Can I have 10 of these kind of jelly beans? Now imagine you're paying an employee $10 an hour. And this person, the customer said, I want 10 jelly beans. Okay, so they carefully count out 10 jelly beans, put them in a bag, charge them, and then they wait around. And then then it gets more popular and more popular. Now you got a line of people there, and somebody says, I want 100 jelly beans. And I like this kind right here. Now imagine you're paying somebody a lot of money, and they're going 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. All right, and the line keeps getting longer and longer. As the owner of the jelly bean store, you say to yourself, something's wrong. This is not going to work. And somebody else orders 3,000 jelly beans. Oh, no. I'll have customers leaving because they had to wait in line so long. So what do you do? What do you do to solve this problem? How can I wait on a customer who orders 3,000 jelly beans almost as fast as one that ordered 10?
Make a pre-order.
You could. I like that. What is it? Right. So here's what we do. Now this book only took 10 jelly beans, but if it's my company, I'd probably take a couple hundred jelly beans, random jelly beans, and I'd weigh them. I'd weigh every one of them. And did every jelly bean weigh exactly the same? No. Does every isotope of hydrogen weigh exactly the same?
No.
Does every isotope of carbon weigh the same? No. Those are my jelly beans. Now, if you took a couple hundred jelly beans and you found out their average mass, what's the average mass of one jelly bean? And let's say it was 5.011. Let me ask you this question. which jelly bean actually weighed 5.011? None of them. Which carbon atom weighs 12.011? None of them. That's the average, isn't it? But if I get a scoop of jelly beans, if I use the average, I can weigh them. If the average of that is 5.011, and I put in there and you say, how many you want? Let's say you want 1,000 jelly beans. What am I going to do here? Ready? 1, 2, 3. I'm going to get my balance, my electronic balance, and put 5,011 grams. 5,011 grams right there. Put them in a bag. There you go. So I never did count the jelly beans, did I? But I feel pretty certain that I did it right. Now, what you don't want to do, and you ever heard of a baker's dozen? In bakeries, they want to go fast too because they had lines, and they'd say, I want a dozen of these little donut balls, okay? Okay, now, wait a minute. Was that 11 or was that 12? So what did they usually do? Oh, I'll throw another one in there. So a baker's dozen was called 13, wasn't it? And that's just because nobody wants to get home and say, hey, there's only 11 of them in here. You cheated me. You ever go to McDonald's, get McNuggets, you're supposed to get like 6, and you only get 5. Doesn't it make you angry? What happens when you get 7, though, instead of 6? All right. My lucky day. So anyway, what they have is you don't want to make the customer angry. So I'm sure in the world of chemistry that this number has changed over time. And with better measurements, we now know. I had somebody do this for an extra credit project once. They found an actual picture of a periodic table in the 1800s. And then they found one in the early 1900s, mid 1900s, 1970, and even 2000. And they noticed that these decimal numbers changed by a little bit as our measuring techniques got better and better and better. Get that? All right, so we're going to count atoms by not counting them, by weighing them. Are you with me? Once they knew about this, and here's yesterday's lesson, okay? Remember, I was just in the world of numbers, number of particles. That's called the mole world. Now watch this world. Here's the little world, and it has to do with mass. One atom of hydrogen has a mass of 1 mu, and one atom of carbon happens to be around 12. And this is about 12 times heavier than that. I got it. Now give me the same number of hydrogen atoms again, 1,000 and 1,000. Okay, I weigh more, and I weigh more. But it's about 12 times more than you. And then go down here. What if I give you this weird number? I'm going to give you a whole bunch of them. This is like way beyond a billion. A billion is 10 to 18th, isn't it? It's way beyond that. All right, so this is almost a million billion. And if I give you that many atoms of hydrogen, it'll weigh a whole lot of AMU, just a whole lot. And if I give this many atoms of carbon, even more. And this mass will be 12 times heavier than that. But here's the key. If I do give you this many hydrogen atoms, it'll be so many AMUs, it will also equal, what? 1 gram. So when I look at that periodic table, and I see that of 1, or 1.00797, I know that means two things. The average mass, everybody look at me for a minute. The average mass of one hydrogen atom is what? It's about what? 1 what? Yeah, don't ever say grams. One atom of hydrogen has a mass of about what? What else can that number mean? If you give me not one atom, but if you give me what? If you give me how many? 6.02 times 10 to the 23rd atoms of hydrogen, that would equal what? It's 1 mole. It's also how much? 1 gram. What if I give you this many carbon atoms? It would equal 1 mole, but how many grams? 12. Yes. Look at me. You're doing it. I never was taught that. I was never taught that. Most people, even if you go to college, I bet most people don't know that number stands for two things. One's in the little world, isn't it? With AMUs. And one of them is in, if you give me a mole of it, that's how many grams it is. Now, look at this right here. How many ways, see, that's what they wanted. They wanted to be in the world of number of particles. Get that? Look at this right here. There's 2 ways to interpret this. What's the little world way of saying this? 2 what? 2 what? I'll draw them for you. Oh, I am sorry. 2 molecules of hydrogen, that's H2. Here's one molecule, here's another. 2 molecules of H2 will react with what? 1 molecule of O2, and what'll happen? Rearrange, it'll make what? It'll make one of those? No, it'll make 2 of those, won't it? Okay, now what's interesting to me is, and I was never taught this either. How else can I interpret it? With this little thing I was trying to show you is that whatever is happening in the gram world is also happening in the AMAU world, wasn't it? And look at what's here. How else could I interpret this? Let's say I had not 2, but I had 2 million of these. 2 million of these would react with what? I need your eyes right on me, okay? 2 million of these would react with what? 1 million of these and produce what? 2 million of those. Watch now, be careful. 2 moles, that's even more than 1 million, isn't it? 2 moles of hydrogen will react with what? 1 mole of oxygen to make. And guess what? When you're in the mole world, I can put it on the balance. How many grams would this be? Each hydrogen has 2 moles of H2, okay? Here's H2, right? Would that weigh 1 plus 1? All right, 1 plus 1 times 2, all right? What's that? So 4 grams of hydrogen will react with, how much is an oxygen? A mole? A mole of oxygen is how much? And don't say AMUs, I'm in the big world. 1 mole of oxygen is how many grams? 16, 15.9. Now, if I round to 3 sig figs, it's going to be 16, right? So 1 mole of oxygen is 16. I got 2 of them, right? I got 2. So that'd be 32. And how much is a water? How much would a water weigh in the big world? Let's see, 2 H's, 1 plus 1 plus 16. There's 18. 18 times 2 is what? Look at this right here. This was the key. They knew this. Before they knew about the world of particles, before the mole theory, they knew that about 4 grams of hydrogen would react with 32 grams of that and make 36 grams of water. I can reduce this. Let's go ahead and reduce this, okay? Watch. Let's divide by 4. Or another way of saying it is 1 gram of this would react with 8 grams of that and produce what? 18 grams of water. See that? They knew that ratio. They just didn't know how many particles it was. So the mole concept let them go from the big gram world into the world of particles. And then they could figure out what everything was made of. Now, maybe you thought I talked too long about the mole concept. You said, just let's get on with it. Now, I understand. But I never really understood the theory behind the mole concept. Okay, so let's get into some of the mathematics. What I'm going to do is, remember factor label?
Yes.
I only taught you enough factor label in the first semester to be able to do factor label problems. I said, you don't even know what a mole is, and you could do a mole problem, couldn't you?
Yes.
So what we're going to do is, the key to factor label is equivalence, isn't it? So here's what we're going to do. We're going to learn about mole equivalence. Now, I've seen other people, high school teachers, even college books, I've seen them teach this differently. I've seen them get so involved. I guess when I first started teaching it, I did like other people did it, because I thought, well, they've been teaching a long time, and I haven't. And so what happened is, I learned, though, as I was going through, I said, wait a minute. If I teach this, and they know how to do factor label, they can do every one of these problems. They can do all of them. So what I'm going to do is start out with anything that is an element. Okay, so for elements, what is the mole concept for elements? So pick any element you want. I'll do one. What you want to do here? For carbon, all right, we're going to do carbon. Is that an element? Okay, so ready? Here are the 3 mole equivalents I want you to know. 1 mole carbon. You know what I think's really weird? You know it's really weird? Sometimes humans do great things, and sometimes they do weird things. Do you know there's an abbreviation for mole? Do you know what it is? MOL. Isn't that kind of weird? It was only 4 letters to begin with, and they thought they needed an abbreviation for mole, MOL. And then later we're going to have to write the word molecules. Guess what the abbreviation for that is? It doesn't have one. Ah, see, they wasted it. They wasted this. Anyway, by the way, the name mole came from a German scientist, and the German word for particle was molecule with a K, molecule. And anyway, so he made the word mole out of that. Anyway, so 1 mole of carbon equals, and remember this in the first semester? 1 mole of anything is what? It's a lot of them. It's a lot of pieces. What is it? 6.02 times 10 to the 23rd. Oh, this is important. What do you put after that? If it's an element, what's the smallest piece of an element? What's the smallest piece of an element that still acts like that element? Atoms. Okay, that's important, okay? 1 mole of carbon is equal to this many atoms of carbon. And now I go to the periodic table. And again, I like to use 3 sig figs. How many grams would that be? How many grams of carbon would that be? And about 12.01, okay? 12.01 grams. Are you with me? Now, I want you to pick another element. So somebody who said, I got an element. My favorite element is
Lithium.
Lithium. Let's do lithium. Ready? Ready? 1 mole of lithium equals, do you know what goes next? Go ahead, write it down. If you know what goes next, write it down. What do you think? So now you know the mole equivalents for every element on the periodic table, as long as I give you a periodic table, don't I? Is that right? What are you going to do with it? What are you going to do with it? Okay, we'll make up a problem. Let's do an example problem. All right, let's see. I think I'll pick, what do you want to do? You want me to give it to you in grams, atoms, or moles? Tell me what you want. What do you want to start with? Anything you want. Sarah, pick one. What do you want to pick? We're going to start with moles. You want me to start with atoms? You want me to start with grams? Moles? All right, give me a number, like weird number. 14? 14 moles of, do you want to use carbon or lithium today? Okay, 14 moles of carbon, and what do you like to convert that into? Do you want to convert it into atoms or grams? Grams, okay. So here's my problem, and we're ready to do factor label. So here we go. What's the first step in a factor label? Sorry, what's the first step? Write down the given. 14 what? Moles of carbon. All right, that's the given. And what's step 2? It's always the same. Multiply the given times a conversion factor. Where do you get a conversion factor? You build them from equivalence. Now, tell me about the equivalence of carbon. Now, I got 3 up here, right? But I can only use 2. Which one do I use? Now, watch now. What label up here has to be canceled out? And then automatically that goes down here. You see it? What would you like to change it into?
Atoms.
No. Look at the problem.
So
What's the problem say? It says change it into grams, doesn't it? So what? So we'll put grams up here. Hey. Now, ready? How do we put the numbers in? Go look up here. Go look. What's this say for moles of carbon up here in the equivalents? No. No. Yes. What number? Okay. Now go grams. No. No. Yes. And when do I put equals? I put equals when the last label in the numerator is the one that I want. It is. That's what I want. Now pick up your calculator. In this case, it's going to be 14 times 12.01. All right, and if you don't mind, I'm going to have everybody round these to 3 sig figs. So go ahead and multiply it and tell me what you get. Somebody's already got it, I bet. No, huh? The only time I use scientific notation is if the number's like not like between 1 and 100. I mean, you could if it's between 1 and 100. I'm okay not moving it in there, but yeah, I would do scientific notation if it's huge. Well, let's go ahead and do scientific notation. I'm gonna do it. Go ahead, scientific notation. What do you got?
1.68
Times 10 to the what?
second.
Okay. And the number after 8 is less than 5? Okay, so we were going to not chop off, but round to 3 sig figs, right? Did everybody get that? Did everybody get 1.68 times 10 to the second grams of carbon?
Yes.
If you don't, just say, no, I didn't. Okay, now, does this take you back a little bit? And said, yeah, I can't remember how to do that. All right. So now I'm going to draw a line. And not only do you know how to do mole equivalents for elements, all right, you know how to do problems with like that, don't you? All right, now we're going to go for compounds. Okay, now for compounds, the first kind of compound I'm going to do is a covalent compound. You say, what was that? I remember that word. What does it mean to be a covalent compound? Non-metal, non-metal. So they want to share electrons, don't they? They don't want to steal. Nobody's going to turn into ions or anything like that. Now, are you ready? Let's do the mole concept for covalent compounds. Probably the simplest one you could do is water. 1 mole of water. Is that a covalent compound? Is this a non-metal, non-metal? Okay. Now go ahead. Here we go. 1 mole of water equals... Remember the word dozen? If I said, here's a dozen baseballs, do you ever ask yourself, how many is that? No. Because you heard the word dozen so much, you know it's 12, don't you? If you're a chemist and I said, I'm going to give you a mole of water, how many is that? No. You don't question how many a mole is. You question how many a dozen is? We don't question how many a mole is. It is 6.02 times 10 to the 23rd. We don't have to worry. I don't understand how many a mole is. What? What if I said a pair? Do you understand that? Yeah, it's 2. Hey, what about a dozen? Yeah, it's 12. How about a gross? You know what a gross is? It's a dozen. 144. Okay? All right, here we go. 6.02 times 10 to the 23rd. Now this is where you have to be big boys and girls. What goes after this one? It's not atoms. You know why? Because it's not an element. There's no such thing as an atom of water. Yes. So there's your special word that goes after a covalent compound. And now, remember, from the periodic table, we're going to get this thing over here. And how much is it going to weigh? Let's think. I have an H, I have an H, and I have an O. H is going to be 1 gram, H is going to be 1, and and O is going to be what? How much? 18 what? 18 what?
It's 15.
15.99.
Yeah. No.
So if I round to 3, if I round to 3 sig figures. Now, I'll tell you another vocabulary word. We have a lot of vocabulary words on the next test. Does anybody know what special name would be given for the amount of the mass it takes to make 1 mole of something? What would be a great name for how many grams it takes to make a mole? What is it? Maybe, but how about the word molar? Molar mass. What's this one? Molar mass. What's molar mass again? It's how many? It's the gram. How many grams it takes to make what? Oh, I lost you. Hold on. It's how many grams it takes to make what? 1 mole of that substance. All right, you try one. Let's pick another covalent compound that you know pretty well. Let's do a hard one. Let's do glucose. 1 mole of glucose. I'll put glucose, okay? What do you put here? It's not hard. 6.02 times 10 to the 23rd. Sorry, what did I put after that, though? Molecules of glucose, right? Everybody know glucose? And now, now what? How many grams? What's the molar mass of glucose? Let's see. 6 times 12, because carbon is 12, isn't it? And how many carbons do I have? 6 times 12 plus 12 times 1. Hydrogen weighs 1, doesn't it? Plus 6 times, how much does oxygen weigh? 15.99. 15.9. So use your calculator. This will be 72, 12, 96. Is that right? And if we add that up, that's good. Look at that. That's a lot of them.
1.8.
How much?
1.8 times 10 to the second.
Right. So about 180 grams, right, of glucose. What do you think? Okay, now let's do an example. All right, let's do a little harder one. How about that? 1 billion molecules of glucose equals how many? We did grams last time. Let's do moles. How many moles of glucose? Okay, ready? Let's try it. Go ahead. Go step 1. What's step 1? What's always step 1 in factor label?
Well, they give it.
How do I write this? That's my given, right? Is that right? Now, on my conversion factor, what label has to be down here? What label do you have to get rid of? Okay, so it's got to go down here then. Oh, I am sorry. You know what? I know what happened. I magnified this from my other class, and I'm running out of space. There we go. All right, thank you. Ready? So this one has to go down here, doesn't it? And what do you want to change it into? Moles. All right, now go shopping and tell me what number. Where do you get these numbers from? Not from the problem. No. Where do you get these? From the what? Equivalents. So go find the equivalents and tell me what goes up here. What goes with molecules of glucose? All right, thanks. What goes with molecules of glucose? Look up here. Oh, there you are. We'll put that right down here. Okay, got that all set. Now what goes with moles of glucose? No. Oh, yes. 1. Just 1. Now, you should get this problem right But you know why you maybe miss it? I tried to teach this to you in the first semester, but why are you maybe going to miss this even though it's a simple problem? Because you have to learn how to talk to your calculator. You want your calculator to take this number and you want to divide it by that number, don't you? Don't you? But if you talk to it wrong, it won't do it. So what do you have to do when you have a scientific number in the denominator? If you divide by that number and you don't put it in parentheses, you will be off by 46 powers of 10. Here's what your calculator, if you don't put a parentheses around that, here's what your calculator thinks you said. 1 times 10 to the 9th divided by 6.02. It'll do that. As soon as you say times 10 to the 23rd, whoop, it thinks you means you're back up in the numerator, doesn't it? And that's why your answer will be out by 46 powers of 10. So what do? 1 times 10 to the 9th divided by parentheses. 6.02 times 10 to the 23rd, parentheses, enter. All right, do that. You don't have a calculator? Oh, you don't, okay. Now, when you get your answer, you look at your neighbor and show your neighbor what you got and put in scientific notation. And let's see, I'm going to give you 1 billion molecules. So how many moles is that? Man, that must be a lot of moles. Really? You think so? I'll give you a clue. It takes more than 1 billion to be a mole. It's not even going to be a mole. All right, Sally, what do you have?
1.66 times 10 to the
10 to the what?
negative 15.
15?
Yes.
Did everybody else get that?
Yes.
If you didn't, if you have an answer that's 46 powers of 10 different than that, then we know what you did. One more time. 1 times 10 to the 9th divided by parentheses. 6.02 times 10 to the 23rd, parentheses, enter. All right. Now, can I ask you something? Did you know ahead of time it was going to be less than a mole? I don't know. I didn't. Think about that. I'm going to give you 1 billion of something, isn't it? But how much does it take to make a mole? How many does it take to make a mole? A whole lot more than 1 billion. So I knew I was going to give you less than a mole, didn't I? So that answer is reasonable to me. That's a very reasonable answer. Okay. Hang on just a minute. Let me see what time it is. This is Wednesday, right? All right, you got to go. All right. Have a nice lunch. Have a nice lunch.